Hello guys, welcome back to Mezon African Motives, still on our Mechanotechnics N5, and this is the flywheels are working with the fly wheel. If you check this part, it's actually our our angular motion. So what I want you to do is to just have a recap for your engineering science N4, the part of angular motion. All right, so if you check on the videos that I did there on science, there's a video that I did on the introduction of the angular motion. So what I want you to do is to go through that video. It's actually as it is. That is your flywheels as they are. So I'm just going to add one or two things, but the rest, just check those that video. I'm going to add one or two things as we are referring. So here when you're dealing with the flywheel, definitely we have the concept of motion. All right, it's either we are talking from the linear and the angular motion. So we also talked about that from our angular motion. We talked to linear, a condition whereby you've got the linear and you've got the part of what of the circular motion. I'm not going to talk about this much. So when we've got the linear, I've got u representing our initial velocity. Remember, this is your initial velocity. So on this, on the circular, it is going to be referred as omega 1, v representing our final velocity. And on this side, this will be referred to as what? As omega 2. So there we've got what? We've got omega 2 there. All right, so we talk of the time. Remember the time, t in seconds, t representing the time. All right, which is the same thing on this side, is just t. Another thing, maybe talk of the displacement. This one is angular displacement, theta. The acceleration, this one is angular acceleration. All right, so we talked about this, all the units, the rad per square second, the radians for theta, the time in seconds, this omega measured in rad per second. So I just want you to go through that angular motion of your N5, of your N4, so that you'll be able to have a recap. So I'm not going to talk much on this part. Like I said, we need the application. So there are some symbols, that one or two that maybe we can just add. The moment of inertia, yeah, that one we never talked about it from our dynamics there. So let us just talk about this. We've got the moment of inertia. So the moment of inertia is measured in kilograms times square meter, which is actually a product of mass and mass times k squared. So inertia is equal to mass times k squared, where k represents the radius of gyration. The radius of gyration, I don't know how do you pronounce this, but it's the radius of gyration, like this. So it is the radius in meters. So that's where we've got the meter squared there. Then the m representing the mass. So this is our mass in kilograms. All right, we talked of alpha, the angular motion. We talk of a for linear, that is the linear acceleration. Remember, n, your rotational speed in revs per minute. We talk of d representing the pulley diameter, r representing the radius, the kinetic energy, potential energy, the displacement s, all those things, you know them. So it's not like something new. So let us get through the questions and see how we are supposed to attempt this. But it's your angular motion from your science N4, like I said before. Okay, so there we are given a flywheel accelerates uniformly from this speed of in revs per minute. So this is our N1 from. So we are given N1. It is starting at N1, 150 revolutions per minute. Take note, it's an acceleration which is happening there to a speed of 1000 revs per minute. So the question was to calculate the angular acceleration. Angular acceleration, remember, it's what? It's alpha. We talked about this from our angular motion. Remember, I said, if you check for the formulas that I listed there, yes, it's true that I say that the angular acceleration is omega 2 minus omega 1 over the time, the change in angular velocity over the time. But remember that our omega is equal to 2 pi n over 60. And I extended this formula and say that it's going to be given as 2 pi n2 over 60. So instead of this, we're just going to write this as 2 pi. All right, we're going to have n2 minus n1 like this over 60t. All right, so that was the formula that I ended up showing you guys to say whenever you're given your speed in revs per minute, this is the best formula for you to use to calculate your angular acceleration. Yes, you can convert, guys. You calculate your omega 1, you calculate your omega 2 from these speeds that you're given. Because if it is omega 1, I just have calculate omega 1. Okay, it's gonna be 2 pi times n1, which is 150 over 60. I calculate, I get the answer. I do the same thing for omega 2, I get the answer. But instead, I can just use the formula like this. Having my speed, I just need the formula there. All right, so there we are given, we are supposed to have a time here. They are saying the number of what, okay, the time of frame of what, 2 minutes. So the time is 2 minutes. Remember, time in seconds, you're going to multiply by 60, which is 120 seconds. That's 120 seconds for time. So there we're just going to substitute everything that we are given. That is 2 pi into n2, which is 1000, minus n1, which is 150, everything over 60. All right, this is 60 times the time. In seconds, the time is supposed to be in seconds, which is 120 seconds. So that'll be 120 seconds. So there we have got our alpha, which is the angular acceleration that is going to give us 0.742 rad per square second. So you just need the formulas there, angular, just like angular motion. All right. Then the number of revolutions made in by the flywheel in 2 minutes, given the same time that we have, but we need the number of revolutions. So if you check from this textbook, the way that they actually answer this question is not the way that we are supposed to have it. Because in order for us to have the number of revolutions, remember, we talked about this from our science N4. We said 1 revolution is equal to 2 pi radians, which is a complete revolution, 360 degrees. So in order for us to have the number of revolutions, we need something that is measured in radians. And what is it? It is the theta, the displacement. Remember, theta is measured in what? In rad. So meaning to say we need to have the theta from what we are given. All right, from what we are given, we need to find theta. And remember that theta representing our angular, that is the displacement. When we are given this omega 1 and omega 2, theta is equivalent to, do we have the time? Yes, we've got the time. So theta is equivalent to the average velocity, that is omega 1 plus omega 2 over 2 times the time. So this is the formula that you can use to find theta in radians. But like I said, the omegas, these ones, they can be written in terms of n. So that means theta in terms of n is going to be given as 2 pi into n1 plus n2 like this over these 2 is going to multiply with 60. So it's going to be 60 times 2. This 60 is for removing the revs per minute to revs per second times the time. So this is the formula that you can use when your speed is in what? Is in revs per minute. But if you're given this in rad per second, you're going to use the rad per second. So this is when you're given speed in revs per minute and you obtain your theta in what? In rads. So that is it. You can take this formula or you can extend it that way. So since we are given this and I do not want to convert this, I'm just going to use my formula straightforward. My N1 in this case, what is the value of N1? 150, N2 is 1000. So this is 150 plus 1000, everything over 60 times t. All right, sorry for that, 60 times 2, sorry, times the time, which is the time that we are given in this case. We are given in how many minutes? In 2 minutes. So take note the time there we are given in 2 minutes, which is 120 seconds. So we are supposed to multiply this by 120. So we are supposed to be very, very careful in your simplification, how you are given your questions, because one, this is what I need you to understand. Formulas can be given in different ways, all right? Formulas, they can be given in different ways. So I'm going to also talk about this. I'm going to talk about this when you're answering question papers, all right? When you're answering question papers, at least that it can help us. It can help us. All right, anyways, no problem. So this is our theta, which is, in this case, on your calculator, you're going to get 2,300 pi, like this. This is your theta in radians. But I'm saying that the theta that we are finding in radians, the purpose of this is to find the revolutions. Why? If you are to consider what we said what we said actually before, we said 1 revolution is 2 pi radians. So in this case, we've got 2,300 rad. That's what we have. 2,300 pi radians. And for each revolution, that is equivalent to 2 pi radians. What about this one? 2,300, they are going to be equivalent to what? 2,300, right, is equivalent to how many revolutions? We do not know. So that will be this over this. It's 2,300 pi. There was a pi there. So it is going to be 2,300 pi over 2 pi times 1 revolution. So there we're going to tell how many revolutions are you going to have at the end. There we're going to tell how many revolutions are you going to have at the end. So this was going to give us something like 1,150. So this was going to be 1,150 revolutions. Revolutions. Okay. Now this is the case. Now this is the case. We can avoid all these unnecessary calculations that happened here. Remember what we need are revolutions. So, okay, we know your answer. Know your answer because I'm just going to take you back to this one. It just hope you understand. Okay, instead of us having this, we can simply go back here and say, how are we given the speed? The speeds that you're given here, it is given in revolutions per minute, in revolutions per minute. So it follows that in a particular time, in minutes, the number of revolution, the number of revs is equivalent to the average speed times time. So it's going to be average speed times time. So we can actually have it in this way. So if the speed here is in revs per second, your time is supposed to be in seconds so that you get the revolutions like this. Revolutions per second times a second is like this. It cancels, you get revolutions. So if this is in revolutions per minute, if this now becomes per minute, it means the time must be in per minute. Revolution per minute times per minute. This cancels. You are left with what? Revolutions. So the average speed must be revolutions per minute for a time to be in minutes to obtain number of what? Of revolutions. So what is the average velocity? The average velocity is N1 plus N2 over 2. That's the average speed. So you're going to multiply by 2. You're done. Your average speed in revolutions, 150. That's our N1 plus 1,000 revolutions per minute. Everything over 2 like this times the time. Like I said, if this is revs per minute, this time must be in minutes, and we are given our time in what? In minutes, which is 2 minutes. So here you use time as 2, not seconds. You use as minute because this is revs per minute. So you are going to obtain again 1,150 revolutions. So these are revolutions, not revs per second, not revolutions per second or rad per second. They are complete revolutions. How many revolutions? That is the question. How many revolutions? That is the question. The question is asking you for how many revolutions, not to say we're going to have our answer as rad per second. No, it's not going to be like that. So I hope we are together there. So these are different questions. We're just gonna try to work as much questions as we can, but as you can see, that's it. Let's check and see. Another part, just wanna see how do they ask these questions. But like I said, revise your angular motion from your N4 engineering science. You will see that there's nothing that is new. All right, on this example, we're given a flywheel with a mass of 50 kilograms. So we are given a mass of 50 kilograms on our information and a radius of gyration, which is 250 millimeters. So like I said, I don't know how do you pronounce this, but just take it as the radius of gyration. 250 millimeters, if we divide by 1,000, that will be 0.25 in meters. And it rotates at 150 revolutions per minute. We are given the speed in revolutions per minute. Calculate the kinetic energy. Okay, so this one, we never had it from our dynamics. So I'm going to explain the formulas that you need whenever you're calculating your kinetic energy. Remember, from the basics of our engineering science N2, yeah, we talked about kinetic energy, half mv squared. That's where we started with this from our science N2. Half mv squared, we are given mass and velocity there. This is for linear motion. But as we extend now that we are having an extended formula when you are dealing with what angular motion, whereby we are going to have our kinetic energy as half of the inertia times omega squared. So this is for a circular. When you're dealing with a circular motion, this will be half I squared, half I omega squared, which is the inertia times the omega, which is our angular velocity. But we know, or explained that before. I just hope maybe I did not remove that formula, or already I erased. All right. But I talked about this inertia, that the inertia is given as the product of mass and the radius of gyration, like this squared. So this here, I is given as mass times the radius of gyration squared, that is mk squared. So this is what you have. So we can substitute this because we've got the mass, and we also have the radius. So meaning to say our kinetic energy can be written as half. In place of this, we're going to substitute mk squared. So this is our inertia. And omega, we do not have omega. And I said omega is in rad per second. As long as we're dealing with rad per second, it means our omega is 2 pi n over 60. Remember how you convert from rad per second, from revolutions per minute. These are revolutions per minute to rad per second. You're going to use 2 pi n over 60. But it's omega squared. It's a squared. It's being squared. So this here representing our omega is going to be also squared. You square this. So that is the formula for the kinetic energy, which is measured in joules. So with this formula, we can substitute because we've got everything. That is half times the mass, which is given the mass of 50 kilograms. The radius is given as 0.25. So that's 0.25 squared times, in this case, we're going to have a bracket of 2 times pi times n, the speed in revolutions per minute. Remember, this was 150. It's a 50 there. So this is 150, everything over 60 squared. So this is going to give us the kinetic energy in joules. All right, so if we were to simplify this properly, we were going to obtain our kinetic energy as 385,531. So this is 385,531 in joules. So that's the idea. That's the idea. So you see, it's now just a matter of manipulating your formulas. You have another formula, you build that formula from another one. So don't be limited to say, this formula that I know does not work. No, generate another formula from another one. You build up that formula to give you exactly what you want to calculate depending with the information that you are given there. All right, another question we are given on example number 3, that is to calculate the torque required, all right, to increase the speed. So there is a change in speed, but there's an increase there. So you're supposed to calculate what? To calculate the torque required to increase the speed of a flywheel with a mass of, so you're given the mass of 1,200 kilograms and a radius of duration, which is 800 millimeters. If we divide by 1,000, the radius is 0.8 meters. So the change in speed, remember the speed was increased from this speed to this speed in revolutions per minute within a time frame of 36 seconds. So we're given N1 from this speed. So we are given N1, 120 revolutions per minute to this one. That is your final speed, 180 revolutions per minute. In 36 seconds, the time, you're given the time, 36 seconds. All right, so this is the idea. When you are to calculate torque, I'm going to also explain about the formulas. All this, you just need to know the formulas to use. All right, so it follows that as we understand our torque, we talked about this, which can be given from the inertia. You are given inertia times what? Times angular acceleration. All right, but which is, remember, the angular acceleration is the change in velocity over the change in time, this one. The change in angular velocity over time. So it simply means our torque is going to end this inertia, this one, we said it's mass times radius squared. So you're going to multiply to this, which we said is the change in what? The change in the angular velocity, that is omega2 minus omega1 for an increase. If it is a decrease, it's omega1 minus omega2. So it's going to be omega2 minus omega1 because it's an increase, this one. That is the change in what? In angular velocity, the change in velocity over time. That is this one. So we have to calculate omega1 from N2. We have to calculate omega1 from N1. But remember, we said we can once with this one, we can substitute again. Yes, you can do your calculations aside. Or just substitute because you know that omega is equal to 2 pi n over 60. So you can substitute this 2 pi n2 over 60 direct on your formula so that you get exact answers. The mass is there, 1,200 times the radius, 0.8 squared, into what? Omega2, which is 2 pi n2. So you're going to have 2 pi n2. N2 is what? 180. Over what? Over 60. Minus omega1, which is 2 pi n1, which is 120. Over what? Over 60. So this is it. You can even calculate these ones on your formula. You can calculate them aside. I'm just showing you guys different ways of doing it over the time, which is 36 seconds. So that this is going to multiply whatever that you're going to have from this one. That's, you get the torque in this case, all right? So from these calculations, you were going to obtain the torque of 134. This was going to give you 134.041 in Newton meter. Remember, torque is measured in what? In Newton meter. Also, you could have manipulated or changed this direct formula. Okay, I just hope you understand. Just going to do that. When you're answering question papers, I'll end up giving you a lot of formulas and you get confusion at the end of the day, because there are so many ways of answering these questions. So just hope with time, you'll be able to check on our videos so that you learn more questions or more ways of answering these questions. On example number 4, we are given a flywheel initially at rest. Initially, it is at rest. Is subjected to a constant angular acceleration of, meaning to say there's an increase in what? There's an increase in speed. All right, let's take note of what is happening here. So it is at initially, remember initially omega1, that's 0 rad per second. That is subjected to a constant angular acceleration of, meaning to say there is an acceleration in that period of 1.8 rad per square second. For 55 seconds, meaning to say given the time frame in this interval, 55 seconds. The flywheel is then decelerated So meaning to say this one, it's a phase. We have got the first phase, we have got the second stage. On the first stage, this one, it was going up, it was accelerating like this, going up. So it is going to start at omega 1, which is at 0, to a certain omega there, omega 2, which you do not know. So we do not know this omega 2. But once it reaches that speed, it starts to decelerate. It starts to decelerate. So what does it mean? At the second stage, when it now starts to decelerate, the omega 2 of our previous question, this one, is our omega 1. So on this second stage that we are now, this one, our omega 1 is equal to omega 2 of first stage. Of the first stage, meaning to say we have to calculate this. That value is the one that we're going to substitute here because we do not know, we haven't calculated that. So we need that value here. All right. Then it is decelerated from that speed that we do not know until it comes to rest. 72 seconds later, until it comes to rest. That's our omega 2 is going to be at 0 rad per second. At rest, there's no movement in the time frame of what? Of 72 seconds. So like I said, this is in stages, stage 1 and stage 2. So they are saying here, calculate, that is our first question, the maximum angular velocity attained. Why are they saying maximum attained? Because this, it accelerated up, then it decelerated. So there is the maximum value where it reached because it never went up. It just went up to that point, then it went down. So meaning to say the maximum velocity is the final velocity for the stage 2. That is the maximum velocity because it decelerated later on. It what? Decelerated later on. So meaning to say in this case, our maximum angular velocity in this case is simply omega 2, the final velocity of the first stage. It reached that velocity, then it went down. So that is the maximum. It cannot go any further than that because it went down from there. That was the idea of the question. So if our maximum velocity, which is our angular velocity, is equivalent to omega 2, therefore let us calculate omega 2. How do we calculate omega 2? We are given omega 1. From our linear motion, we understand that V is equal to U plus AT. This is from our linear motion. So from the angular motion or circular, it follows that this V representing our omega 2 is going to be omega 2 is equal to omega 1 plus alpha T. We are now talking of angular, not linear. So that's our omega 2 is omega 1. We started at what? At 0 plus our angular acceleration, which is 1,8 times the time frame in 55 seconds. What is going to be the omega 2? The omega 2 is the maximum angular velocity attained. They are asking them. They are just asking this in another way, but it's the one. So that was going to give us 99 rad per second. So that's we've got what? Our omega 2 from there. So it went up from 0 to 99 rad per second. Then it went down. We do not know, is it going to go to 0 or what? But yes, until it comes to rest. Then it went to 0 again. Then the question is now the angular deceleration. Why are they asking this? Because this is in two phases. The first phase, it was of an angular acceleration. The second stage is now going down. It's a deceleration. But like I said, on the second stage, what we only know is that our omega 1 of the second stage is that omega 2 of the first stage because it reached a certain value, then it went down. So this is now our point 1, our point 2 of the phase 2 or of the second stage. So meaning to say, if it is like that, what we now have here is what? It's omega 1. We have omega 1, 99 rad per second. Our omega 2 is now at 0. Remember, I told that it went at 0. So what is going to be the angular acceleration? I mean, the angular deceleration in this case. They want angular deceleration, meaning to say we are going down. That's a negative. So how are we going to calculate this? We are given omega 1, omega 2, and t. Remember that angular acceleration is the change in angular velocity over the change in time, which is simply omega 2 minus omega 1 over the time. Our omega 2 is the final one. It's now at 0, minus omega 1, which is 99, over the time, which is 72 seconds. So that was going to give us the angular acceleration. So this is our angular deceleration, I mean, because we're going to get a negative here, negative 1,375 to 3 decimal places, 375. This is rad per square second. So this is to tell us that it's a deceleration. The negative that we are seeing there is to tell us that this is a deceleration. If it was a positive, that is we are going up, it's an acceleration. So this is how your questions might be given as. They want you to play around your formulas of angular motion. So like I said, this is direct your engineering science N4 that you just need to work on. Then the C part, they are asking us to calculate the number of revolutions made, all right, by the flywheel during the acceleration and deceleration period, during both. So we can calculate it from the average. Remember, this time we do not have like N1, N2, so it is difficult. So in this case, remember we said the number of revolutions, they can be taken from what? Number of revolutions. They can be taken, can be calculated from theta. Why from theta, which is our angular displacement? Because our theta, which is angular displacement, is measured in radians. And as we understand that in a revolution, we have got 2 pi radians. So that one of average is not going to work. N1 plus N2 over 2 times time. It's not going to work because we do not have that. This time it's not going to work. It's not going to work. So we are left with this one of calculating the angular displacement. Then we make a conversion from there. So how are we going to calculate? Remember, it's between the two stages. The first stage for an acceleration and the second stage for a what? For a deceleration. So this is what you're just going to do. You are simply going to calculate theta for the first stage and theta for the second stage. All right, let me just put it this way. Remember, I said we need to calculate the number of revolutions, which is actually fine, which is actually true. But in order for us to have the number of revs or the number of revolutions, we need theta, which is measured in radians, so that we can make a conversion. So we have to calculate theta here, and we also calculate theta here, so that we have got the total theta, which is going to be from the first phase, just going to be theta 1, from the second phase, which is theta 2, in radians. Then we can convert. Theta is the one that carries the what? The radians. So how are you going to calculate theta from the first stage? It's up to you there. There it's up to you. You can use the area under the graph if you are to draw this half base times perpendicular, because you're going to formulate a triangle, which is fine. Or since we calculated omega 2 and we know that this is 99, remember I always choose this formula even from our N3 hours. We talk about this, that theta is equal to omega 1 plus omega 2 over 2 times t, average velocity times time. We have omega 1, we've got omega 2, we calculated this. So theta from the first stage is going to be omega 1, which is 0, plus omega 2, which is 99. We got 99 there over 2 times the time frame, which is 55. All right? So each and every part is going to work for you. Each and every part is going to work for you. So you calculate this. In this case, it was going to give us something like the problem that I combined. All right, the problem that I combined, you see the problem now, guys. But you're just going to calculate this. All right, let us just add another one here. For the second stage, meaning to say for the second stage, we also have, remember our omega 1 is this and our omega 2. You see my preparation, guys, I combined this on my preparation. So let me just combine 99 plus omega 2, which is 0 in this case, over 2 times the time. In this phase, the time was what? The time was 72. So this is theta for the first stage. This is theta for the second stage. You calculate these separately. All right. Like I said, as for me, I had already combined these So that's the problem. So, but if you are to do this, you're going to obtain the total theta in radians, as this one was going to give us 6,286.5 in radians. All right. The purpose of doing this, remember, is that we can be able to change or to calculate the revolutions, because the revolutions are taken from the relationship between the radians, all right, between the radians and the revolution. If one revolution is equal to 2 pi radians, what about this one that we are given 6,286.5 radians? How many revolutions do we have there? We just have to divide. So is this the number of radians to the radians? Radians to radians times what? The revolutions. So it's going to be 6,286.5, everything over 2 pi times 100. So this will give us the number of revolutions, which is going to be 1,000,527, something like that. So it's an approximation of 1,000 revolutions. It's an approximation of 1,000 revolutions to be made. Okay, so you see, guys, this is how they can ask this. On the number of revolutions, yeah, you have to be very, very careful. So that was the question there. So on the number of revolutions, you have to be very, very careful. The way that you're given, how you're given your question, actually, there you have to be very, very careful. On example number 5, a flywheel has got a mass of 400 kilograms. So if we are given the mass of 400 kilograms, a radius of gyration of 600 millimeters. So that's our K, 0.6 in meters. Calculate A, the kinetic energy required to give the flywheel a speed of, so we've got a speed of 100 revolutions per minute. From rest, that is the change in speed there. The change in speed is just that, what you're given. So there's no effect. I talked about this kinetic energy formula. So guys, this one, we are not going to waste much time. Let me write down the formula. I'm not going to manipulate anything. I talked about this formula manipulated. Remember, we manipulated the formula for kinetic energy, which was taken from half inertia. Let me just write where it was taken from first. Half of inertia, omega squared, and we said it can be given, manipulated as, remembering that inertia is mass times radius squared. Then omega is 2 pi n over 60, but it's supposed to be squared. All right, remember we talked about this, and this is measured in joules. So we're just going to substitute in this case half of the mass, which is 400 kilograms, times the radius squared, the radius of gyration squared, times, in this case, we go to the speed because we're given the speed. Even if it was omega 2 minus omega, from rest. So we are supposed to actually use omega 2 minus omega 1. So if we subtract at 0, there's nothing. So you're just going to use your n as it is. So it's 2 pi times 100 over 60 squared. So you can even use this concept, omega 2 minus omega 1. But you see that you just have got the same thing because we are from the rest. So there's no effect there. So this was going to give us 789.568, which is measured in what? Which is measured in joules. That's your kinetic energy. So questions can be given on this type of a question. They want you to understand, know how your questions are given, this and that. So you have to be very, very careful on your questions. All right. So there we are given another part. This one, it was actually the change in torque. Actually, this one, it was a mistake because the change in torque we are supposed to have the time is different from the kinetic energy where you work without a time. When you're if you check on the formula that we had, we were supposed to use the torque is equal to this. It's omega 2 minus omega 1 over t. And with omega 2, with this, yes, you can find this as omega 1 as omega 2. But to have t, we must have the angular acceleration. And if we are to check in this case, we do not have any angular acceleration that you're going to get. They actually want you to calculate it later on here. They actually want you to calculate this acceleration here, the time required for this acceleration that happened. So if you are to check the way that your book answered, they used revolutions, this one as revolutions, not as revolutions per minute, meaning to say it was a mistake in their setting. They wanted to use as revolutions instead of revolution per minute. So guys, we can't work on that. We're gonna do question papers so that we see how do they ask. I want you to be related on questions. How are they given so that you don't fall into a trap of answering your questions wrongly. All right. Depending on the information that you are given, you are supposed to be very, very careful how you take your information. All right, so this is example number 6. Again, another question which is on the flywheel. All right. So like I said, on the other part, remember theta is measured in radians, not revs per minute. So you don't change this one and say it's now theta. No, there's no magic like that. So that's the error they did there. All right, anyways, let us see this one. What are we given there? Example number 6, we are given that a flywheel of a punching machine has a mass of 1.2 ton and the radius, which is being 1.2 meters. Okay, for the first time to be given this direct in meters. Anyways, let us see what you're given. We've got the mass of 1.2 ton, which is 1,200 kilograms, taken from a radius of duration of 1.2 in meters. And it is rotating at, so this is the speed where it is rotating at, which is 175 revs per minute. And the question was to calculate the kinetic energy of the flywheel. The flywheel possesses the kinetic energy. All right, guys, for the kinetic energy, I think now we are enough on this. So we are enough. As for me now, I'm enough because they are just repeating the same thing. And we talked about this. We said kinetic energy at the end is going to be half of. All right, this is where it started. Then we ended up with the half of mk squared into 2 pi n over 60 squared. Remember, that is what we ended up with. So it's half of the mass, which is 1,200, times k squared, which is 1.2 squared, times, we're going to have 2 pi times the speed, 175 over 60. So this is what we have squared. So if we are to simplify this, it gives us directly the kinetic energy. And that was going to give us 290,166,369, something like that in joules. By dividing by 1,000, that is 290,166 kilojoules. Okay, so that's it. That's it. So you just need to know how you present your formulas, this and that, your formulas. They are very, very important. Then the amount of kinetic energy the flywheel will dissipate if it is rotated at 2. All right, if it is retarded. All right, to retard is to reduce the speed, a deceleration. There is a deceleration that is happening. So we still need the kinetic energy, but there is a deceleration. So whenever there is a deceleration, it follows that you're going to use this formula for kinetic energy. Kinetic energy is going to be half of the inertia. Then we're going to have the change in the speed. The change in the speed. So it's going to depend, are we increasing or decreasing? For a retardation, it's going to be omega 1 squared minus omega 2 squared. For an acceleration, if it was accelerating, it's omega 2 squared minus omega 1 squared. You must take note. Is it retarding? Is it accelerating? All right, we talked about this. So nothing is going to change. It's going to be the same, half of mk squared. We talked about this. How do you calculate it? So it's going to be 2 pi n1 over 60 squared like this. Minus, we also talked about this, 2 pi n2 over 60 squared. So we're just manipulating our formulas to suit in our information that we have. So that's it. With this information, we can substitute whatever that you are given. So it's going to be half of the mass. We have the mass, remember, it was 1,200 kilograms. And the radius of duration is given as 1,2. So that was going to be 1,2 squared into now, remember the speeds that we have. There's a retardation. from this one to this. So this is our 2. This is our 1. 175. So it's going to be 175 there. So it's going to be 2 pi n, 2 pi times 175 over what? Over 60. Minus, you do the same thing. It retarded until what? Until the speed is what? Until the speed is 150 revolutions per minute. That's our N2. 150 revolutions per minute, like this. So this is going to give us the kinetic energy. Sorry, why am I leaving the squared? There's a squared, there's a squared there. So you are supposed to square this like this. All right. So your kinetic energy in joules is going to be 76,000. 982.914 joules. Just divide by 1,000. That will be 76.983 kilojoules. All right, that's it. You have your kinetic energy. You have your kinetic energy. So that's how these questions, they just try to play around. You guys see, how do you freak out? But that's the idea there. Now they're saying the average force exerted on the punch, on the punch, if 70% of the kinetic energy is calculated, of the kinetic calculated in B is required for punching stroke. All right, we need 70% of the kinetic energy calculated in B. In B, this is our B here. This is it, B, this one. So we need how many percent here of this energy? We need 70%. So remember that this here is going to come from what? The energy that we need, the 70% of energy is going to be used as what? And what are we needing this for? This is the work done. The 70% energy that we are talking about is the work done. So we can take advantage because we want to calculate the force, the average force. And we know that average force from the work done, all right? Work done is equivalent to force times distance. That is what we understand. So if we've got the work done, then we can calculate the force. Because we have the distance that was taken in the stroke length, the stroke. So S there is 75 millimeters, 0.075 meters. But what about the force? That is where now we think of the work done, because it's what that's going to help us to calculate what? The force. So work done is the 70% that we are given here, 70% of the kinetic energy. So we also have that same work done. It is 70% of the kinetic energy. So that is 0.7 over 100 to remove the decimal, remember? Times what? The kinetic energy, which is this one. 76.983 in kilojoules. So if you use kilo, it means this energy is also kilo. That's our work done. But this is not enough, because we are saying the work done now is it is force times this. What about the force that we want? Divide by S, divide by S. So it follows that force is work done over distance. So with that now, we can be able to calculate our force from this work done over distance, because we calculated this our work done 70%, which is 0.7 of what? 76.983 in a kilo. So this, remember, is in kilo. So it means our answer is going to be in kilonewton over S, which is the distance, 0.075. For that distance in meters, what is going to be the force? So there we are going to get 718.508 in kilonewton, like I said. That's it. So all this part, it's your angular motion. This is your angular motion, everything there. It's your angular motion. They are testing you that angular motion. Do you know it? Just one or two things that you're just adding here and there, but it's your angular motion. So please, guys, revise as many questions as you can. Another example we are given, a flywheel dissipates 12.5 kilojoules of energy. So the energy dissipated there, that is 12.5 kilojoules, when the speed drops 4.8% below this. So the speed drops, meaning to say initially the speed was at what? 162.5 revolutions per minute. Okay? Which you can convert to rad per second. It's going to be over 60, this 2 pi n over 60, something like that. So if you use this part of 2 pi n, it's going to be 162.5, and this will give us 17.017, something like that, rad per second. So from n, we are calculating what? From this n, we are calculating omega. So it's like we are given omega, which is our omega 1. 17.0171 rad per second from this. But they are saying in this case, the speed it was dropped, or it is what? When the speed drops 4.8 below this speed. So it means our omega 2 is going to be the difference. It's going to be omega 1. If you want to use the rad per second, therefore you use omega 1 in rad per second minus the percentage that we are given there. So it's minus 4.8% of what? Of that same omega 1, because it was just dropped from the omega 1. So that simply means in this case, our omega 2 is going to be in rad per second, which is 17.017 minus 4.8 as a percentage. Guys, you're just going to divide by 100. That will be 0.048 into omega 1, 17.017. Just like that. Just like that. So this was going to give us 16.20018, which is simply 2 in rad per second. Okay. But the question is, was we are simply taking our information here. Remember that. We are simply taking information. This is our omega 2, 16.2 rad per second. Let us just put it like this. Okay. Now we move on to the other part. The radius of gyration, which is K, is given. 950 millimeters, that's 0.95 meters. Calculate the mass of the flywheel. Where can we put the mass? Why are they giving us kinetic energy, which is the one they have been asking us to calculate before? Now they gave us this kinetic energy. They cannot just give us this for granted. They want us to use it. So perhaps there is mass there in kinetic energy, and truly it is there, because remember, we said when there is a change in this, that is going to be half of I. That is the change that is going to be, all right, omega 1 minus omega 2. It's an increase there. So it's going to be omega 1 minus omega 2. So if you are to check here, what it means is that we have this in rad per second, which is fine, but this one is the one that carries the mass. This will be half of, this is half of mk squared. Remember that. This is our formula here. Okay. So that means truly I can calculate the mass. I just have to divide by this. Right? I can remove these 2, yes, by multiplying by these 2, which is fine. I can just multiply by 2 here. This cancels with this. So that means I'm left with 2ek. The kinetic energy is equal to m k squared into omega 1 minus omega 2. So since I want the value of m, I can divide by this. So that will be 2ek divided to this. I'm going to divide by this and this. So it's going to be k squared into omega 1 minus omega 2. So this is now a substitution taking place. The mass is equivalent to 2 times the kinetic energy that we are given before, 12.5 kilojoules. So this is kilojoules. Remember, it was you who was converting your own answer. So when you write it, you just write as it is, 12.5 times 10 to the exponent of 3. It was our calculation, yes, it was our conversion, but we have to write the joules as they are. The K is 0.9 0.95, but this is k squared. So it's 0.95 squared times omega 1 minus omega 2 from those differences that we had. This is 17, remember we calculate this, 17,7017 and 16,2. You find the differences between these two. 17,017 squared minus 16,2 squared. Guys, why is that? I'm simply forgetting this omega squared. Guys, please forgive me. This one I'll end up having a wrong formula. Think this now. I'm just tired now. I just need to end up this video. All right, let me just finish up and end up this video, guys. It shows that I'm now tired. All right, so this is our mass here. If we are to simplify this, we are going to obtain 969,692 kilograms. Okay, so that's your mass. That's your mass. Okay. Then they further on say that the torque required to increase the speed from rest to this. All right, so this one, it was a tricky question here because what happened in the first place, it was our omega 1 was this. Remember, it was at 162,5. This was our omega 1. So we actually had omega 1 like this. But now they are saying the torque required to increase the speed from where? From rest to this. This is no longer our omega 1. No, we are having another condition. Our omega 1 on B is another thing. From rest, from 0 rad per second to this one. Increase to increase, means say there's an increase there to that 162,5. Which is 162,5 in revolutions per minute, is the one that we converted before, remember? And it gave us 17.017 meters rad per second. This is omega rad per second. So that's the idea. It's a change of what was there previously. There we started with omega 1 as that speed to another speed. Then they are saying, no, start from rest to this. But we calculated this before. Given the time frame of 55 seconds, what is going to be the torque there? All right, we had a formula for torque also. I said that, I don't know if I talked about this one, but I think I mentioned this formula that the torque is equal to the moment of inertia times the angular acceleration over, all right. Why is it that I'm just, there's nothing that we are dividing here. If we want to divide is when we're going to take this, but we have this. All right. Remember I want this torque. And this, we have the mass, everything. We calculated this actually. I, we have it. I, we have it. Remember I said I is mk squared. So we have this. But we do not have the angular acceleration when it is from this to this. We have to calculate this. From these three, how can we calculate our angular acceleration? From this is time. We are given time, omega. Remember, omega 2 is equal to omega 1 plus alpha t. From V is equal to U plus AT. And us, what do we need there? We need this alpha. So we're going to transpose, it's going to be omega 2 minus omega 1. We divide by what? We divide by t. So the moment we divide this by t, we are left with angular acceleration. So that's our angular acceleration, which is going to be omega 2, 17.017 minus omega 1, which is from where? From rest. So from the rest, our omega 1 is 0 over 2 over t. The time frame that was taken there was 55 minutes. So that was going to give us 0.309 494. All right, something like that. Rad per square second. So with this formula for torque that we have here, I think we can just substitute. Yes, I. Remember, I, you said it's mk squared, of which we calculated I, isn't it, that we have I, or we calculated that I. All right, this is, we never calculated this. We just have the mass. But from here, we can just substitute. Remember, we got the mass, so you're just going to substitute and use our mk squared. So this is our torque, and this can be just written as torque is equal to mk squared of alpha. So remember, the mass is the one that we calculated here on our first question. That was 969.962. All right, so this is 969.692 times k, the radius of duration, which is 0.95 squared times alpha. The purpose of this calculation of this alpha, it was because we need it here. So now that we have it, let us just write it. 3094. So that's our torque in this case, which is going to be 270.77 in Newton meter. That's the torque. So these are the typical questions. These are the typical questions. So I want you to try as many questions as an individual. Try to understand how questions are given. How are they given? And do as many question papers from there. But for now, that's it, guys, for Meson African Motives. Till we meet again.